Hello class, we're going to be looking at chapter 4.1, Writing and Balancing Chemical Equations. Rockets use solid fuel. They're mixtures of substances combined in carefully measured amounts and ignited to yield thrust-generating chemical reaction. It's just saying that these need to be balanced properly so you know the ratios that you mix together. Okay. Well, so our objectives here: writing and balancing chemical equations, derive chemical equations from narrative descriptions of chemical reactions, write and balance chemical equations in molecular, total ionic, and net ionic formats. Okay. The preceding chapters introduce the use of element symbols to represent individual atoms, molecules, and components. A balanced chemical equation uses symbolism to represent both the identities and the relative quantities of substances undergoing a chemical or physical change. Let me back up a second. Physical changes can be represented by these chemical equations also, like H2O in the liquid state, and then an arrow goes to H2O in the gaseous state. That would be an example of a physical change, but written as a chemical equation. So this is the reaction between methane and oxygen to yield carbon dioxide, and, that should have been an and, water. It may be represented by a chemical equation using formulas. Top. Okay, so here's methane plus oxygen, but it's saying that these represent molecules. So this is one molecule of methane. It's reacting with two molecules of dioxygen, that is O2, and it reacts to form carbon dioxide and two molecules of water, H2O, or dihydrogen monoxide. So this is what it would look like using models. You have a molecule of methane, two molecules of dioxygen, and you break these apart. You take the hydrogens off of the carbon and the oxygens, you separate those, and you take two of those oxygens and you slap them on carbon, and you get carbon dioxide, and the other two oxygens, you slap all the hydrogens on it, and you get two molecules of water. So there's a balance between the atoms that go into the reaction and the atoms that come out. Hence, the reaction is balanced. This example illustrates the fundamental aspects of any chemical reactions. 1. The substances undergo a reaction are called reactants, and their formulas are placed on the left side of the equation. The substances, okay, let's go back a second. These are the reactants. They're on the left side of the equation. The substances generated by the reaction are called products, and their formulas are placed on the right side of the equation. So these are products. Plus sign separates individual reactants and product formulas, and an arrow separates the reactants and products, the left and right sides of the equation. The relative numbers of reactants and product species are represented by coefficients. That is, these numbers, this number right here and this number right here. Of course, these have coefficients of 1, but they're just not written because 1 is the identity. Okay. So coefficients are the numbers placed immediately to the left of each formula. A coefficient of 1 is typically omitted. All right. Coefficients. It is common practice to use the smallest possible whole number coefficients in a chemical equation. Those coefficients represent the relative numbers of reactants and products, and therefore they may be correctly interpreted as ratios. Previous example, methane and oxygen react to yield carbon dioxide and water in a 1 to 2 to 1 to 2 ratio. Regardless of the absolute number of molecules involved, the ratios between the numbers of molecules are the same as that given in the chemical equation. So, 1 unit of methane always reacts with 2 units of oxygen and yield 1 unit of carbon dioxide and 2 units of water, regardless of what those units are. In this case, it's 3. The unit is 3. The chemical equation described previously is balanced. That is, the equal numbers of atoms for each element are represented on the reactant and product sides. The number of atoms for a given element is calculated by multiplying the coefficient of any formula containing that element by the element's subscript in the formula. Okay, let's go over that again. The number of atoms for a given element is calculated by multiplying the coefficient of any formula containing that, not only of any formula, of all formulae that contain that element by the element's subscript in the formula. Okay, so let's back up. Boom, 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 boom. The number of oxygen atoms here is not only the 2, but it's also times the 2 for how many oxygens are in that particular compound, how many oxygen atoms are in that compound. So as we see, this represents 4 oxygen atoms. And similarly here, there are 2 molecules, but there are 2 hydrogens per molecule because of the subscript. So this represents 4 hydrogen molecules and 2 hydrogen atoms, and 4 hydrogen atoms and 2 oxygen atoms. Okay, boom, 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 boom. All right, so that's what the number of atoms for a given element is calculated by multiplying the coefficient of all the formula that contain it by the element's subscript in the formula. If an element appears in more than one formula in a given side of the equation, the number of atoms represented in each must be computed and then added together. For example, both product species in the example reaction CO2 and H2O contain the element oxygen. So we have to calculate the number of oxygen molecules there are in the 1 carbon dioxide molecule, which is going to be 2 atoms, plus the 2 atoms that are in the 2 water molecules, 2 oxygen atoms, and so it's 4 oxygen atoms total. The equation for the reaction between methane and oxygen to yield carbon dioxide and water is confirmed to be balanced as shown here. CH4 plus 2O2 yield CO2 plus 2 H2O. The element in the reactants, you've got 1, back up. That should have been a 1. In the hydrogen, there are 4, because there's 4 times that. The oxygen is 2 times 2 is also 4. The products, it's one carbon atom, there are these two oxygen atoms and these two oxygen atoms, so there are 4, and the the 4, and the hydrogen comes from here. There are 4 of those. So does 1 equal 1? Yes. Does 4 equal 4? Yes. Does 4 equal 4? Yes. So the equation is balanced. An unbalanced chemical reaction can be balanced by a fairly simple approach known as balancing by inspection. So we simply take what we're given, an unbalanced equation, and test it to see if it's balanced. So in the reactants, the number of hydrogens is 2, the amount of oxygens is 1. In the products, the amount of hydrogens is 2, and the number of oxygens is 2. So it's balanced on the hydrogen side, but not for oxygen. So you got 1 atom of oxygen here going to 2 atoms of oxygen. The number of H atoms are balanced, but the number of O atoms is not. To achieve balance, the coefficients of the equation must be changed as needed. Subscripts define the identity of the substance. So it means we're not going to be changing these things, H2O, H2, and O2, because those define what the substances are. What we will be changing are the coefficients. So subscripts define the identity of the substance, and so these cannot be changed without altering the qualitative meaning of the equation. The O atom balance may be achieved by changing the coefficient for H2O to 2. So now we have the amount of hydrogen on the reactant side is 4 hydrogen atoms. The amount of oxygen is 2 oxygen atoms. On the product side, we have 2 hydrogen atoms, and we've got 2 oxygen atoms. But it's not balanced for hydrogen, but it is balanced for oxygen. So putting that first coefficient in there balances oxygen, but that's all. The H atom balance was upset by this change, but it is easily reestablished by changing the coefficient of H2 to 2. So now we've got 2H2O goes to 2H2 plus O2. So we check. The number of hydrogens on the reactant side is 2 times 2 is 4. On the product side, it's 2 times 2 is 4. On the oxygen on the reactant side is 2 times 1 is 2. And on the product side, it's 1 times 2 is 2. So yes, 4 equals 4 and 2 equals 2. These coefficients yield equal numbers of both hydrogen and oxygen atoms on the reactant and product sides. Therefore, the equation is balanced. It is sometimes convenient to use fractions instead of integers as intermediate coefficients. So this is ethane plus, this is what it would be in one of the gases in natural gas. So this is running a Bunsen burner, plus 7 halves O2 yield 3 H2O and 2 CO2. Essentially, you looked at this and you said I needed 7 oxygen atoms in order to make these products. But oxygen doesn't come in atoms, it comes as diatomic, and so therefore the 7 oxygen atoms became 7 halves molecules of O2. When balance is achieved, all the equation's coefficients may then be multiplied by a whole number to convert the fractional coefficients to integers, multiplying each coefficient by 2. 2 ethane molecules plus 7 dioxygen molecules gives rise to 6 water molecules and 4 carbon dioxide molecules. So this is balanced and this is balanced, but this is preferred because we have integer coefficients. The physical states of reactants and products are often indicated with a parenthetical abbreviation following the formulas. So we know that sodium, solid sodium, when it's thrown into water, gives off hydrogen gas. So you have sodium as a solid plus H2O as a liquid gives rise to sodium hydroxide, which will be dissolved in water, aqueous, plus H2, which boils off as a gas. Special conditions necessary for a reaction are sometimes designated by writing a word or symbol above or below the equation's arrow. For example, a reaction carried out by heating may be indicated by the uppercase Greek letter delta over the arrow. So that delta is supposed to represent a flame, basically. It means you heat it, and this undergoes this change. And this is calcium carbonate. Under heat, can be turned to calcium oxide plus carbon dioxide. Many chemical reactions take place in aqueous media. Big way of saying in water. When ions are involved, the chemical equations may be written with various levels of detail. We have the molecular equation, and that's what we've been dealing with in lab. So in this is an example that calcium chloride, which dissolves evenly in water and becomes aqueous, will react with 2 formula units of silver nitrate, which also dissolves in water and it is aqueous, and it gives rise to calcium nitrate, which is also dissolves in water, it's aqueous, plus silver chloride, which precipitates out of solution as a solid. And so you have 2 clear solutions are mixed together and a solid falls out of it. So these labels indicate the states of the chemicals. Molecular equations don't explicitly represent the ionic species that are present in solution. When ionic compounds dissolve in water, they may dissociate into their constituent ions. So calcium chloride, aqueous, is the same as writing calcium 2 plus aqueous plus chloride minus aqueous. And of course, the 2 is there because that's what arises from it. Silver nitrate, 2 silver nitrates, aqueous, actually means that the silver ion is aqueous and the nitrate ion is aqueous. Oops. And calcium nitrate means that the calcium ion is aqueous and the nitrate ion is aqueous. Unlike these 3 ionic compounds, silver chloride does not dissolve in water to a significant extent. So it's a solid and it does not dissociate into ions. Ionic compounds dissolved in water are more realistically represented as dissociated ions. So we can and we have represented these reactions, like in the copper lab, with the molecular compound, the molecular reaction. But what we're going to do subsequently is represent the go from a molecular reaction to a total ionic reaction. So that same reaction that we had back here of calcium chloride aqueous and silver nitrate aqueous goes to calcium nitrate aqueous and silver chloride solid. It can be represented this way. It's called a complete ionic equation, where you say that the calcium chloride has dissociated, so it's actually present as calcium 2 plus ions and chloride minus ions, and the silver nitrate is present as silver plus ions, aqueous, and nitrate minus ions, aqueous, and that goes to calcium 2 plus aqueous plus silver nitrate, 2 nitrate ions, aqueous, plus silver chloride solid. Two chemical species are present in identical forms on both sides of the arrow, the calcium 2 plus aqueous and the nitrate minus aqueous. These species are called spectator ions because they just sit around and don't do anything. They just look at everything else going on around them. Ions whose presence is required to maintain charge neutrality and are neither chemically nor physically changed by the process. Those are spectator ions. Elimination of the spectator ions from the equation results in the net ionic equation, that silver ions, aqueous, react with chloride ions, aqueous, to form silver chloride solid precipitate. So this is the net ionic equation. We go back here. This is the molecular equation. This is the complete ionic equation for that same reaction. And this is the net ionic equation for that same reaction. And that is our lesson for today. Thank you very much for listening.